said at equilibrium, what happens to our delta G? Our delta G is equal to 0. And what are the factors we listed can affect chemical systems in equilibrium? Change in concentration. Okay, change in concentration. And number 2, change in pressure. Number 3, change in what? Temperature. That are the 3 cardinal things. We have other things that can affect it, you know, but these are the main cardinal ones. Okay. I have this reaction. This is a contact process where I have SO2. You know contact process now? SO2 plus what? Oxygen, giving me SO3. Up here? I think the temperature should be minus 395.7 kilojoule per mole. If I'm right, yes. And the catalyst I'm using is V2O5. What is the name of the catalyst? Vanadium 5 oxide. What is the name of the catalyst? Vanadium 5 oxide. Okay, can we balance this? Where should we balance? To where? Should we put 2 here? Is it balanced? No. 2 where again? 2 here. Okay. Still not balanced. Is it balanced? Is it balanced? Oxygen here is how many? 6. 6. Sulfur 2. Okay. Then I want you to give me the conditions that will increase the yield of SO3. This is a practical industrial process. We call this thing what? Contact process. Is it prayer? There's one school called SHIM, School of Health Information and Management. Your prayer point is you never enter that school. In Jesus' name, say amen. Amen. There are the people making noise there. Every time. This is their habit. I don't know what they do in class. They can come and discuss a full movie and make noise. And you see them in the hospital. Oh, we'll continue. So, tell me the conditions. Write 3 conditions that will increase the yield of SO3. What did I say? Write 3 conditions. 3 conditions that will increase the yield of SO3. Then I have another process. This is number 1. This is number 2. In this process, I have nitrogen plus, remember this is gas. We should indicate the state. This is gas, this is gas. I have nitrogen and the hydrogen. They gave us what? NH3. Is it balanced? Eh? Okay, what is this process called? This one is called what? Haber. Haber process. Okay, I'll add 2 here. And I'll add what here? 3. Is it complete? Eh? Yes, is it complete? Okay. Now the catalyst used here is finely divided ion catalyst. Eh? Okay. Ion catalyst, Fe. Then the temperature, I think minus 46.5 kilojoule per mole. I think, I'm not very sure, but I know it's 46.5 kilojoule per mole. So you also write the conditions that will increase the yield of ammonia. Is it complete? Wow. I think we should start writing. Eh? Eh? You did not read. Okay, thank you. Just let me give them a few minutes before I start writing. I hope these questions I'm doing are not here. Definitely not. Okay. There's one that is here. That's Expo. Have you seen the two reactions? Okay. Let's analyze this. Just, are we together? Are you sure you're with us? Eh? Are you with me? Where are you? Are you far? We wrote two reactions. Number one is contact process, where we have SO2 reacting it with air to get what? SO3. And I said that the delta H, what is delta H? Eh? The heat change, that's the enthalpy, is minus 395.7 kilojoule per mole. We've written this established. They will give you in your exams. Then now they ask you, write three conditions that will increase the yield of SO3. Sulfur oxide. Do you know the three conditions that will increase it? You have to look at these things. See the things you must look at. You look at what? Concentration. You look at what? Pressure. And you look at what? Temperature. Remember that our state of matter is very sacrosanct, please. But possibly you did not read this. How many of you read it at home? How many of you understood the topic? How many, if you did not understand, raise up your two hands. The Lord is watching you. Eh? The Lord is what? Watching you. Eh? Are we together? I just write this thing and don't write anything again. Just three conditions. Three. Okay. What is the total volume here? 2 plus, which is what? 3. 3 volume or 3 moles. What is the total here? 2. Are you listening? Stop writing. Just look at your screen. If you are closer to your screen. Increase in let's start with concentration. And when you see concentration can be increased and concentration can be decreased. Hello? And let's see the things you can. These are, do you know the reactants? SO2 and O2 are the reactants. And what is the product form? SO3, the product. Okay. You must know this. I can increase the concentration of SO3. I can increase the concentration of oxygen. I can increase the concentration of what? Eh? SO3. I can increase the concentration. Okay. Now, this is the stoichiometry of this reaction. What is the stoichiometry of this reaction? This is 2:1:2. That's the stoichiometric ratio. 2 is to what? 1:2. I can decrease the concentration of this one, true or false? I can decrease it. I can decrease this one. Now, if I increase the concentration of SO2, what will happen to the equilibrium position? It will what? Shift to the right-hand side to favor the production of what? SO3. I say 3 conditions. At least you've gotten one. What is the first condition? Increasing the concentration of what? SO2. If you increase the concentration of SO2, what will happen? It will shift the equilibrium position to the right-hand side to favor the production of SO3. We say when you increase the concentration of the reactant, the equilibrium position will favor to shift the concentration of the product. Okay. This is number 1. If I increase the concentration of this, what will happen to the equilibrium position? It will shift to favor this one. Now, don't write. I know you want to write. If you increase the quantity of oxygen or air, what will happen again? It will shift again. It will shift to favor the production of this. Now, listen. If you increase the concentration of SO3, what will happen to the equilibrium position? It will shift to the what? Left-hand side. Now, if you decrease the concentration, if you decrease the concentration of SO2, what will happen? It will favor the what? Left-hand side to replenish, to do what? That thing you are losing. Are we together? So if I reduce air, what will happen to this thing? It will shift to this side. If I reduce SO3, this is just like in a company. I have SO2 react with O2, and they are giving me SO3. I keep removing SO3. So once I keep removing SO3, they will be producing more of what? SO3. If I keep removing oxygen, what will happen? It will reverse. But if I add SO3, what will happen? Will it favor this side? Where will it favor? Thank you. So, what are the 3 conditions that will increase the yield of SO3? Let's list all the conditions. Number 1 was increasing the concentration of what? SO2. Number 2, increasing the what? The quantity. The quantity of what? Air. Increasing the quantity of what? Air. Increasing the quantity or volume of air, which is O2. And what else can we do again? We are discussing on concentration now. First is what? Concentration. Increasing the concentration of what? SO2. Increasing the quantity of what? Air. Still on concentration. Decreasing the volume of what? Thank you. Is that the spelling? Decreasing the conc of SO3. What are we working on now? Concentration, because all these things, they have roles to play. They have what? Roles to play. So once you consider concentration, consider it for everything. If I increase the concentration of SO2, what will happen? There will be more of what? Are you together? Is somebody not understanding us? Now, if I increase the quantity of air, what will happen? The guy there. Oga on spec. If I increase the quantity of air, what will happen? Are you taciturn? Maybe it's your eyeball. I'm not seeing well. Once I increase the quantity of air, what will happen to the equilibrium position? It will shift to... You see, I've discussed this guy. I've discussed this guy. Now, remaining this guy. Will I increase the quantity of this guy? I need to what? Decrease the quantity. You move. Go to the second point. Which is what? Pressure. Which is what? And for pressure to act, I don't know who is writing. There are things we must check. What are the things? Thank you. You must check the state. At least one of the reactants or products must be in what? Must be in what state? Gaseous state. Now, all of them are in gaseous state. Oh. But we said at least one. Can pressure act? Yes. Secondly, we say there must be an equimolar difference in the reactants and the what? Product. What is the total volume here? 3. What is the total here? Can pressure act? Can pressure act? Then we can discuss what pressure will do. And for pressure, you can increase pressure or what? Decrease pressure. So if we choose to increase the pressure of the system, what will happen? Increase in pressure favors where there is reduction in volume. Say it. Again. While. Thank you. So, for us to increase the yield of SO3, what do we need to do to pressure? Yes. So we are going to increase the pressure of the system. We are going to do what? Now listen. Pressure is not concentration. Because concentration, I can choose to increase the concentration of this, concentration of this. Pressure is either if you increase, it increases for everybody. If you decrease, it decreases for what? Everybody. Don't say increasing the pressure of SO2. Where is it done? Or increasing the pressure of oxygen. Or decreasing the pressure. No. Are we together? So if I increase the pressure, it is going to favor the place where there is reduction in volume. If I do what? If I increase the pressure, it will favor where there is reduction in volume. Class, where is there a visible reduction in volume? SO3. So if I increase pressure, there will be more yield of what? SO3. If I increase pressure, there will be more yield of what? SO3. Because of what? Pressure favors where there is reduction in volume. And we have 2 and 3 here. So increase in pressure will favor this guy. Okay. Then consider temperature. Consider what? Temperature. We established there's something about temperature which we are going to do. Temperature can increase, can shift the equilibrium position and also affect the equilibrium constant. And I think we'll discuss equilibrium constant after now. So, but for temperature to act, or for you to know where temperature will favor, at least you need to know the heat change in the overall reaction. What is the heat change accompanying this overall reaction? Is it minus? If it is minus, it is what? Exothermic. If it is minus, it is what? Exothermic. Now listen. We established that increase in temperature will favor what part of a reaction? Say it. Increase in temperature favors the endothermic part of the reaction. If you are not talking, you're a suspect. Say it again. Again? While I had the increase. While you cannot be Obwenye and Amosu. So you must be attentive to locate the endothermic part of the reaction. And we established that if the forward reaction is endothermic, if the forward is endo, the backward must be what? Exo. If the forward is exo, the backward must be what? Endo. And the enthalpy change they will give you in the exam is the enthalpy change for the forward what? Reaction. For the what? Forward reaction. So what is the enthalpy change here? It is exothermic. Up here? It is exothermic. So what will favor exothermic? Eh? Thank you. So I'm going to write here decrease in overall temperature of the system. Decrease in what? I need between 200, 400, and 450 degrees centigrade to achieve this. For just 200, 400, or what? 450. Which is anything from, is the temperature is very low. Very, very low. So, what are the three conditions that will increase the yield of SO3? Number one, increase in concentration of SO2. Two, increase in the volume of what? Air. Number three, oh yeah, the next point, increase in what? Pressure, overall pressure of the system. And lastly, decrease in overall temperature of the system. Is anybody confused? Eh? Is anybody confused? For the last time, if the forward reaction is endothermic, what will happen to the backward reaction? Now, decrease in temperature, which part will it favor? Eh? Decrease in temperature will favor the exothermic part of the reaction. Now, take this down to Haber process. Now, I'm giving you 1 minute. Process this. What are the conditions that will increase the yield of ammonia? Delta H is 46.5. I know it's 46 point something, even if it's not 5, but I know it's 46 point something kilojoule per mole. What are the conditions that will increase the yield of ammonia? I will check the people at the back. Write the conditions that will increase the yield of ammonia. That's if you know the one that is ammonia. Ammonia is the one with NH3. Write the conditions that will increase the yield of ammonia. Your own must be quite different from your neighbor's work. You and your neighbor should not write the same thing. A1 smashed. A1 smashed. Ah? Nyamia. Which one? Increase in the quantity of air. And where be air nearby? Air? Or air? Hydrogen is not air. You represent air with O2. You represent air with O2. And the part of that air that is active is the oxygen. You don't represent. But you cannot say air. Is air anything? Everyone smashed. The people at the back shock me now. Someone should clean the board. All right, equilibrium constant. Equilibrium constant, Kc. Equilibrium constant, Kc, can be defined. Equilibrium constant, Kc. I'll put my own Kc. Equilibrium constant. Can be defined as the ratio of the concentration of the product as the ratio of the concentration of the product Madedego to the concentration of the reactant. To the concentration of the reactant. Each raised to their each raised to their respective stoichiometric coefficient. Each raised to their respective stoichiometric stoichiometric coefficient at a given temperature. Have you written something? Or you define equilibrium constant, Kc. No, now. Let the choir be organized. I want you ready to go. What is equilibrium constant? I know it's stating a late from what you know. I close your note. Look at the board. Look at the board on your screen. If you are bending down with an error, anti on big spec. Touch her. Oh yeah. What is equilibrium constant? Ratio of the concentration of the product to the concentration of the reactant, each raised to their respective stoichiometric coefficient at that given what temperature. Oh yeah, right heading equilibrium law. Equilibrium law. Equilibrium law. Like the rate law. Like the rate law. Like the rate law. The equilibrium law. The equilibrium law is based on the law of mass action. It's based on the what? Law of mass action by Cato Maximilian Goubert. By Cato Maximilian Goubert and Peter Wage. By who? I read what you've written. The rate law is based on what? The law of mass action. So who stated the law of mass action? That is what? Cato Maximilian what? Goubert. And what? Peter Wage. We call it the law of Goubert and Wage. I just gave you the full name. Cato Maximilian Goubert and who? Peter Wage. Which states that the rate of a reaction is directly proportional the rate of a reaction is directly proportional to the concentration to the what? Concentration of the species involved. Of the, okay, use active. Of the active species involved. In the reaction. We call it the law of mass action. The law of what? Mass action. We say that this equilibrium law is based on the law of mass action. And who gave us the law of mass action? By who? Just call it the law of Goubert and Wage. Forget about Cato Maximilian Goubert. What is the law of mass action? What does it state? The rate of a reaction is directly proportional to what? In the reaction. Again, can we state it? So who is the owner of that law? Goubert and Wage. The rate of a reaction. Okay. Let's still move to our hypothetical reaction. A plus B give us what? Hypothetically. Is it real? And they are all gases. Okay. See what this law is saying. Can I add coefficient? Later, I will introduce the coefficient. That the rate of this forward reaction, rate of the what? Forward reaction is directly proportional to the what? Concentration of the active species involved. Okay. So the rate of the forward reaction is directly proportional. What are the species involved? What are the species involved here? The species involved here is A times what? This is times. Of course, you can decide not to add it. Times B. Or where? The rate of the forward reaction is directly proportional to the active species involved. See the active species involved, A and what? B. You know, if I have a solid or a pure liquid, if I have what? A solid or a pure liquid, they are not active species. So I cannot involve them here. Had it been I indicated this thing as solid, say solid, the rate of this reaction will be equal to what? Will be equal to what? B. Do you get? So why did I include this A? Because it is what? An active species. And for it to be an active species, it should be what? A gas. So if you have a solid or a pure liquid, it should be a gas or maybe something that is not a pure liquid before it can be an active species. So I have A and what? B. Thank you. They cannot even see me there. Okay. The rate for the forward reaction, I need to introduce an equal to, is equal to the rate constant for the forward reaction. The what? Rate constant for the forward reaction times A and what? B. We've settled the forward reaction. All right, let's see the backward reaction. The rate of the backward reaction will be directly proportional to what? Did you get this first step? No. Rate for the rate of the forward reaction is directly proportional to the what? Active species, to the concentration of the what? Active species involved. What are the active species? This is the forward reaction now. A plus B will give us what? So these are the reactants. Now, the rate of the forward reaction, I need to introduce a constant now, and I will introduce the Kf, which is the rate constant for the forward reaction over what? Times A and what? B. All right, what is the rate of the backward reaction? It's going to be what? C times what? D. Up here? Now, RF, RB is equal to what? KB times what? Times C D. Okay. At equilibrium, at what? So what happens at equilibrium? The rate of the forward reaction is equal to the what? Rate of the backward reaction. Say this is what happens in equilibrium, where the delta G will be what? So at equilibrium, my RF will be equal to what? RB. And I have my KF here. So, okay. Now, if my RF is equal to my RB, what is my RF? KF up where? A B equal to what is my RB? KB what? KBC times what? D. Are we together? Are we is anything confusing you here? At equilibrium. At equilibrium. Secretary, don't copy now. Just take note. The rate of the forward reaction is equal to the rate of the what? Backward reaction. Okay, if we rearrange this equation mathematically, you are going to get the equilibrium constant, which is, if I write this KF over KB, and I put equal to here. So where will my A plus B be? Mathematically, will it be up? You don't know mathematics. Will it be up? This is KF times A times B. So where will, if I write KF here, will I write A and B up? Where will it be? So when you expand, you get it. Okay? So write A up where? Times B. This is times. And what should be up? C times D. And this thing is equivalent to the equilibrium constant. Is equivalent to the equilibrium constant. And so what will I now say is equilibrium constant? Ratio of concentration of the CD is the what? Product of where? Over the concentration of the AB is the what? Reactant. Any confusion? I copy. Step by step. Copy step by step. When you reach here, you write at equilibrium. The light is having scoy. Don't worry, they will change it. At equilibrium, RF is equal to RB. Take note. Rate of the forward reaction is equal to the rate of the backward reaction. And the forward reaction is this. KF A times what? B. It will be equal to KBC plus D. So KF should go down, while KB comes up if you want to expand this. You know. So, and this is the product, while this is the reactant. It is equivalent to the equilibrium constant, which is product over reactant. So, class, what is equilibrium constant? Define it. I say it again. Is the what? Ratio of the concentration of the product to the concentration of the reactant. Each raised to their what? Respective stoichiometric coefficient at a given temperature. The next thing, I'll add a coefficient to the reaction. So we can raise it to their stoichiometric coefficient. Can you state the law of mass action by Guberg and Wage? 1, 2, ready, go. The law of mass action by Guberg and Wage. I want you ready, go. So we established the ones that are active species. If I have a solid, is it an active species? If I have solid, is it an active species? No. If I have a pure liquid, is it an active species? No. Now, pure solids and pure liquids, their equilibrium constant is assumed to be unity. Is assumed to be what? Is assumed to be what? Some of your textbook can say it's unitary. Unity. Can accept to be what? It can assume to be what? Unitary. Which is what? 1. Which is what? 1. Which is what? 1. So for pure solids is 1. For pure liquids is the same 1. Switch from that junction, the what is it called? Ceiling fan. Number 1 from this end. Switch it off. Number 1 from this end, not the other end. Okay. Are we through with this? Okay, class, what is equilibrium constant? Okay. I'm the one. Okay. Okay, let's add a coefficient to this. Are you listening? Okay. Let me assume this is my M. This is my N. This is my X. And this is my Y. And here I have 2. And here I have 3. So can you write the expression for the equilibrium constant? Can you write the expression for the equilibrium constant? Oh yeah, let's do it. Let's do it. Kc is product. Okay? Over what? Reactant. Oh yeah, what is the product? C and what? D. So this is C2. I will raise it to the coefficient, to the stoichiometric coefficient, which is what? X. Times D raised to power what? Y. Over what? What is the reactant? A raised to power M times He said what? Is it B raised to power 3? Is it B3 raised to power N? B3 raised to power N. Thank you. Raised to power N. Oh yeah. For the hypothetical reaction below, the expression for the Kc is given by, you write this. For the hypothetical reaction below, the expression for the Kc is given by this. For the hypothetical reaction below, the expression for the Kc is given by by this. You write it. Have you written it? This on the board, I want everybody to give me the expression for the forward reaction and the expression for the backward reaction. Give me expression. Just give me any expression for the rate constant. Yes, for the rate constant of the forward reaction and the rate constant of the backward reaction. For this, A, B, C, give me an expression for the rate constant of the forward reaction and that for the backward reaction. Do it like the first one. Are you confused on what to do? Eh? Oh yeah, do it. You start with this. Rate for the forward reaction. Start like this is B plus what? Okay, forward. Forward is what? A. So RF will now be what? K F bracket A. Or you do for the backward. Alright. Is somebody doing it? Yes. For the backward is going to be what? RB. RB is directly proportional to what? B. Is it plus times? Times what? C. RB is going to be what? K. K? What's in KF? KB. B. Times what? C. Or you continue. Is it KC first? K. F. All over what? KB is what? Is it is what? Okay, say this B here. Okay. Times C. over what? A. Okay. Now, what I want you to do, give me the rate constant only for the forward reaction. Give me for the forward reaction. Give me for the forward reaction. Give me for the forward reaction alone. Do you know what I mean? Just give me the expression KF for the forward reaction. Just write it what it will be. Give me the expression KB for the backward reaction. Write what it will be. I want to just tell you what. Okay, what are you getting in this one? Eh? No, you're not doing what I want you to do. The equilibrium constant for the forward reaction is going to be the same thing with this. Eh? It's going to be B times what? C over A. That of the backward will be what? That of the backward will be what? A over B times C. Is this correct? Eh? Check. For the forward, yes, this is correct. For the forward, this is what it will give you. This is for the forward reaction. This is the forward reaction, which is like this. For the backward reaction, okay, for the forward reaction, what will it be? Product of over what? Which one is the product? Product over the reactant. Okay? Now, for the backward reaction, what will it be? This one will now be what? Reactant. It will be what? Product over the reactant. Did you get the gist? For this A reacted to give you B plus C. And the equilibrium constant for the forward reaction should be product over what? Reactant. Now, what is the product? B and what? C. What is the reactant over what? A. Now, what is the equilibrium constant for the backward reaction? It is now going to be what? A. Now, in the backward reaction, what will A be? A will become what? Product. A over what? Reactant. Then you complete it here. The KF times KB is equal to 1. Is equal to unity. Just write it. KF times KB is equal to unity, which is 1. KF times KB is equal to what? Unity, which is what? 1. Note, KF is 1 over KB. KF is what? KF is the reciprocal. Okay? KF is the reciprocal of KB. While KB is what? What is KB? Reciprocal of what? While KB is the reciprocal of what? KF. 1. KF is 1 over KB. 1, that's the reciprocal. Now check here. What is KF here? BC over A. What is KB? A over B. This means just reciprocal. This simply means that KF is A up here times C. Is it B? B times C over what? A. So when I say that this thing is reciprocal, what does it mean? When I say that KB is reciprocal of this, it means 1 over B times C all over what? A. 1 over this. And 1 over this, if you work it, it will become what? A over B times C. Should I explain again? I know our brain went to new market. Just let's understand. Just it's a very small concept, but it always causes wahala. Okay. Listen, I said A will give us C plus what? B. Relax, look at the board. Now, what is the equilibrium constant for the forward reaction? For the forward reaction, what is it going to be? What is it going to be? Product over what? Product over what? Which one is the product? C times B over what? A. Is this one established? Is it established? Is it one confusing? Oh yeah, what of the equilibrium constant for the backward reaction? So it's now going to be product for the backward now. Product over what? Reactant. So A will now become what? You change it. This is the forward. This is the what? Backward. So it becomes what? A over C times B. And I told you, mathematically, this thing simply means that KF is the reciprocal of KB. Is 1 over what? Is 1 over K is 1 over KB. Up here? So what will KB be? 1 over what? KF. It is reciprocal of each other. If you turn this one the other side, you get the other one. If you turn it the other side, you get what? The other one. And I say that KF, the rate constant for the forward reaction, times that of the backward reaction is what? Unity. Is what? Unity. Meaning, let's times it. C times B over what? A times what? A over C times what? B. Let's check whether it's equal to 1. This guy will cancel this one. This guy cancels this one. This guy cancels this one. What do you have? 1 over 1, which is what? 1. So, at any point, the KF times that of the KB must be equal to what? 1. Must be equal to what? 1. Okay, I write it. I don't know how you start writing this, but find a one and write something there. Then after writing it, you write relationship. This is the most important thing I want you to write. KF times KB is equal to unity. You are going to see it in theoretical questions. Hmm? It should be what? Is it KF? Yes. It is not even F first. It's B. Share? Mm-hmm. So reciprocal, this is KB now. Once you add one on top, it changes to KB. Uh-huh. So once you add one, this one goes up. This one comes down. This KB is not KF. This is the final product now. KF is this normally. Then 1 over this, it changes to KB. And if you express it normal, KB will now be, this A will come up over B times what? C. Do you get? Uh-huh. Just small thing you alter in KF, you get KB. Okay, right. Relationship between KC and KP. Relationship between KC and KP. Relationship between KC and KP. Right, KC and KP. I said, you know, some of your textbook, you will not see it as KC. You see it as what? KP. But they are different things. So write relationship between KC and KP. Right, KC and KP are equilibrium constant. KC and KP are equilibrium constant of ideal gaseous mixture. Have you written it? KC and KP are equilibrium constant for ideal gaseous mixture. Are you still copying? Eh? KC and KP are equilibrium constant for ideal what? Gaseous mixture. Right, KC is expressed or KC is used. KC is used when the concentration are expressed in molarity. KC is used when the concentration is expressed in molarity. KC is used when the concentration is expressed in molarity. Why Kp is used when the concentration are expressed in atmospheric pressure. Have you written it? Right under it. Kp, right under it. Kp is the equilibrium constant when the partial pressure of a gaseous reactant, when the partial pressure of a gaseous reactant and the product are considered at equilibrium. I read what you've written. Start from the relationship between Kc and Kb. 1, 2, ready, go. What? Of an ideal gaseous mixture. So when we use Kc, when the concentration is expressed in terms of molarity. When do we use Kp? Is expressed in terms of what? Partial pressure. Atmospheric what? Is the same thing. Now I read the next line there. Kp is the equilibrium constant. Okay. Let's say I have A plus B giving us, okay, let me just say C. 2C, 2A, gas, gas, gas. And we are asked to express the equilibrium constant in terms of partial pressure. So what are you going to do? Express the equilibrium constant in terms of partial pressure. So what you are going to write K what? P. Equilibrium constant in terms of partial pressure is going to be P squared. P what? Squared. C inside. Do you get? Yes, now. In the other one, what is it going to be? If in terms of Kc, it will be Kc equals C raised to power what? 2. In terms of partial pressure, what is it going to be? P squared. Where? In bracket what? C over partial pressure squared A. Where? Times partial pressure of what? B. Full stop. I expressed it in terms of what? In terms of partial pressure. But can you express this in terms of Kc? When you express it in Kc, you are talking about the molarity. Is it hard to express? I express this one for me. Express the production of ammonia for me in terms of partial pressure. The production of ammonia is nitrogen plus hydrogen will give us 2NH3. Is it balanced? Where do we need to balance? 3 here. Is it balanced? Or yeah, express this thing for me in terms of Kp. Express it for me in terms of Kp. Express it for me in terms of Kp. Let me get questions. Okay, I've seen few questions. So what is it going to be? Kp is what? I have P squared NH3 over P bracket N2 times P raised to power 3 bracket H2. Full stop. You see the difference between Kc and Kp? Very slight difference. Okay. Express A plus B will give me C plus D, M and N, X and Y, all gaseous. Express it in terms of Kc and also express it in terms of Kp. Is it a hard thing to do? Okay, in terms of Kc for this guy, for Haber process, it's going to be what? NH3 raised to power what? 2 over what? Over what? N2 times what? H2 raised to power what? 3 in terms of concentration. This guy is in terms of partial pressure. So express this thing for me in terms of concentration and in terms of partial pressure. Have you done justice to that? If you are confused, raise up your hand. You don't know how to express this thing. Eh? You don't know how to do it. Never lay hand on that guy. The second, switch this one on. That's this, the one you're looking at. Yeah, keep it at 5. It's okay. Just express it. I saw it in your exam. It was open to me. like a screw. Is it hard? Is it hard? Have you done it? Am I eager, me? Am I eager, me? But do you know what to do? You know what to do? Do you know what to do? Do you know what to do? Hey, we are in class and we are learning. Auntie, do you know what to do? And let me see what you are doing, because you are as confused as your plain paper. You see, simple thing, simple, like it's 1, 2, 3. I'm even tired, and some people don't even know how to express it. All right, look. Let's do it together. Let's do it what? Together. All right, stop writing. Those ones that don't know what they're doing, it's okay. You are the ones that is still writing. In terms of KC, what is equilibrium constant? Concentration of the... Which one is the product? This is the product, and this is the what? Our guy at the back. That guy that say he doesn't know what... Yeah, and you will still not know what you are doing because you are still looking at your paper. It is the product over what? Stop writing. No one need the product over reactants. Kita. Second, get the local government. Okay. So what? Nanyeba. The product. Eh? C and what? Thank you. So this C, you raise it to the stoichiometric ratio. What is the stoichiometric ratio there? X. You raise it to X. Then, D. What is the stoichiometric ratio there? You raise it to Y. Over again, reactants. What are the reactants? A and B. So A, I will raise it to what? M. B, I will raise it to what? To N. So I'll finish. This is the KC expression for the equilibrium constant. But in terms of partial pressure, in terms of what? It will now be KP. Up here? Still product over what? Reactant. Now, but now it will be C. What is the partial pressure there? P what? P what? P raised to power X. Times. There's times here, of course. Times what again? P raised to power what? Y. Over again. P raised to power M bracket what? A. Times what? P raised to power N bracket what? B. This is in terms of KP. This guy is in terms of what? KC. Are you still confused? Are you still confused? Oh yeah, let's do this guy in terms of KP. This guy now on the board. Now what is it? KP is going to be what? Product over what? Reactant. In terms of KP, P raised to power what? 2. Bracket what? C. Over P raised to power 2. Bracket what? A. Times P raised to power 1 or just P. In bracket what? In bracket what? B. You can raise it to power 1. You can choose not to raise it to power 1. So far you know what you are doing. All right, for reactions involving ID gases. For reaction involving ID gases, Kc, Kp equals Kc. Kp equals Kc. Bracket RT. Kp equals Kc. Bracket RT raised to power changing N. Just there like this. For reaction involving ideal gases, Kp is equals to Kc bracket RT raised to power change in N. Where change in N is the change in number of moles. Where change in N is the change in number of moles. They will give you where R is the gas. R is the what? Gas constant. R is the gas constant. T is absolute temperature. Have you written that? For reaction involving ideal gases, Kp equals Kc bracket RT changing N. Alright, class, what is changing N? What is changing N? What is R? The gas constant. I think it's 0.082 or something like that. What is T? Absolute what? Temperature. So if I express this thing here, wait, see this. Let me tell you the usage. Kp equals Kc bracket RT. For this expression now, what is the change in number of moles? What is the change in number of moles? Product minus reactant. The change in number of moles is what? X, are you watching this X? Plus what? Y. Minus M plus what? N. Okay, take this question. Let's still use Haber process. Let's still use Haber process. All right, number one. Change in N. Change in N is positive. Change in N is positive. when the amount of gaseous product is more than the amount of gaseous reactant. Change in N is positive when the amount of gaseous product is more than the amount of gaseous reactant, as seen above. If I rewrite this equation to be this way, and I have N2 plus hydrogen is going to be what? 3H2. In this format, look at the board. Which one is the reactant? In this format, which one is the reactant? Eh? Which one is the reactant? Which one is the product? Okay. Let's find the Kp equals Kc. Kp bracket RT change in N. What is the change in number of moles here? What is change in number of moles? Eh? Why is it 2? Here is 2. Here is 1 plus 3, which is what? 4 moles. Here is 2 moles. So this thing is going to be Kp, Kc, RT. The change in number of moles is what? Eh? The change in number of moles is going to be 4 minus 2, which will give you that this guy is 2. Right again. Change in N. Here, change in N is positive. Change in N is positive. Number 2, change in N. Number 2. Have you written this? I copy it. What is the first point you wrote? Read the first thing you wrote. Change in N is positive when what happens? Okay. Right again. Number 2. Change in N is negative when the amount of gaseous product is less than the what? Amount of gaseous reactant. Example: SO2 plus O2 SO3, is it balanced? What should we do to balance it? We add 2 here and add 2 here. Check, is it balanced now? This is the reactant and this is the product. What is the total number of moles here? 2:1. Total is what? Total is what? 3 moles. What is the total mole here? 2 moles. So what will be changing the number of moles? What will it be? It will be what? Is it -1? So Kp, Kc, RT is going to be what? Product minus what? Reactant. 2 minus 3. Okay? Which is minus what? 1. So what happened in that second step? Which one is greater? Number 3, change in N is 0. Change in N is 0 when the amount of gaseous product is equal to the amount of gaseous reactant. When the amount of what? Gaseous product is equal to the what? Amount of gaseous reactant. We have hydrogen, just any reaction, hydrogen plus iodine will give us what? Hydrogen iodide. Should we balance? So we are going to write 2 here. So what is the stoichiometry of the reaction? 1, 1, 2. What is the stoichiometry of the reaction? What is the stoichiometry of this reaction? 2, 1, 3. What is the stoichiometry of this reaction? 2, 1, 2. What is the stoichiometry of this one? 1, 1, 2. So 1 plus 1 will give us what? 2. This is 2 moles and what? 2 moles. So what is this guy going to be? Kp is Kc RT 2 minus 2. Zero. So they will ask you in exam, when is Kp equal to Kc? Yes. When this thing is 0, you will now write therefore Kp is equal to what? Kc. When changing N is equal to 0. So when we change in N be equal to 0, when the number of gaseous products is equal to the number of gaseous reactants. Okay? Change in N will be equal to what? 0. And at that point, what will happen? Kp will be equal to what? Kc. Kp will be equal to what? Kc. When will Kp be equal to Kc? That is how they will ask you that question next year jam. What happens? When change in n is equal to what? 0. Now, when we change in n be equal to 0? Okay. Now, when change in n is greater than 0, what happens? When change in n is greater than 0, what happens? We have 3 scenarios. Listen. The amount of what? Gaseous product is more than. Is it more or less? What did I ask you? When is change in n greater than what? Greater than 0. Change in n will always be greater than 0 when the amount of gaseous product. Now, in this reaction, what is the gaseous product? 4. When the amount of gaseous product is greater than that of the reactant. So when it is greater, the change in number of moles will now be what? 4 minus 2, which is 2. Say 2 is greater than 0. 2 is greater than 0. Now, when will change in n? When we change in n be less than 0? When the amount of gaseous product is less than the gaseous react. What will happen to change in the number of moles? The change in the number of moles will be negative. When it is negative, that means it is less than 0. It is less than what? 0. But when change in n, when change in n is equal to 0, it means that the amount of gaseous product is equal to the amount of gaseous reactant. And what happens at that state? Kp will be equal to Kc. So the question they will ask you, when will Kp be equal to Kc? When what? Change in what? Change in n. What is that change in n called? Number of moles. I write all these things in your notes now. Write 3 things. When change in n is greater than 0. When change in n is less than 0. When it is greater than 0 is positive. When it is less than 0 is negative. And when change in n is equal to 0. These are things you must know. Right? What happens then? You might just forget about the scenario. Forget about the scenario. You might not need to know it. The only thing you need to know anywhere you are is that Kp is equal to what? Kc bracket RT change in what? N. Take this thing everywhere. You must know it at this level. There's another one, but at this level we are not permitted to know that. You must know that Kp is equal to what? Kc bracket what? RT raised to power what? Change in N. What is that R? Gas constant. What is T? Absolute temperature. Oh yeah, when is Kp is equal? When will Kp be equal to Kc? When what? When what? Oh, Sunday. When what? Ndiochazo. When the amount of gaseous reactant is equal to what? the number of gaseous products when their moles are equal. You see that your Kp will be equal to what? Kc. Now, class, what is equilibrium constant? What is equilibrium constant? The choir is disorganized. Ngama the duster now. 1, 2, ready, go. What is equilibrium constant? I am moving. Again, constants can be defined as now, even if you don't know it, stop at this one. Change in concentration of the ratio of the change in concentration of the product over that of the reactant. So if we get it, they will give you your mark. Product case is what? Concentration of the product over concentration of the reactant. But if you now have to be professional, you will know that each will be raised to what? To their stoichiometric coefficient at that given what? Temperature. At that given what? Temperature. Now, what is the relationship between Kc and Kp? Just get that in his ear. Why won't you sleep? What is the relationship between Kc and Kp? Kc is expressed in what? In molarity. Why Kp is the concentration expressed in what? Partial pressure, atmospheric pressure. I think we are ready for the quiz. Okay, my question from my device, when is Kc said to be unity? What is unity? In this, unity is what? 1. In any equilibrium system in which a solid or a pure liquid is a reactant or product, the active mass of the solid or pure liquid is assumed to be what? Is assumed to be 1. Is assumed to be what? 1. Or give me for this guy. CaCO3. CaCO3. Make sure you balance it for me. If you burn it, it will give you quicklime and CO2. This is a solid. This is a solid. And this is gas. Balance this equation first. Then give me the Kc value. Everybody, balance this equation and give me the Kc value. Balance the equation. I know some want to balance it. Is it balanced? Oh yeah. When you decomposed limestone, it will give you what? Quicklime and CO2. So give me the Kc value. Okay, you know Kc value, yeah? Product over reactant. Give me the Kc value. Product over reactant is the Kc, equilibrium constant. Product over reactant. Give me the value now. Kamani job. Kena saruno tigi. Eh? Sense. Say amen. Organa. Kebenge bido. Touch that guy. Touch that guy. On a meeting. Or getting one. Give me the KC value. Are you through? F9. Is it your answer? F9. I know you fail it. Just input in. A1 smashed. A1 smashed. A1 smashed. I don't like going here. Baby Yemia. Show me your own orga. Last born. F9. 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 Many onese odamaduku. How will you get it? Power. Okay. F9 again. F9. You see your problem. F9. Registered. Baby Nyamia. A1 smashed. Ogabago. F9. Dangerous. F9. Dangerous. F9. A1 smashed. Baby Gabago. A1 smashed. Don't put it over. A1 smashed. Ah, baby Nyamia. A1. A1. You see? F9. F9. Okay, it's okay. This is a solid. I told you, this is a solid. Genonte omowa. Listen, the KC value is the product over what? Oh, reactants. Of course, you get me go thinker. But because this is a solid, it is assumed to be what? Unity. It is assumed to be what? Unity. One, if don't consider it. Is this guy a solid? Eh? Okay. So this is going to be what is the product? CaO up here. And the what? CO2. Over what? Eh? Is it not times? Over reactant is this CaCO3. This guy is a solid. Say this guy is a solid. So it is unity. One, remove it from your equation. You don't need it. This guy is what? Solid. It is unity. Remove it. The KC value is just CO2. A1 smash. State the law of Goldberg and Wage. 1, 2, ready, go. The law of mass action now, that is what we explain it. The rate of the what? Reaction is proper to the concentration of the active species what? Involved. Active what? Species involved. Is this guy an active species? No. I told you solids and the pure liquids are not active species. They are not what? And they are said to be unity and constant. They are said to be what? Unity, which is what? 1. So the KC for this is just CO2. And when you see it, you see uncle may over a war. Imagine pure oka. Okay. Do you know about your esterification reaction? Or what happens in esterification reaction? What happens in esterification reaction? Now, just tell me. Oh, yeah, okay, don't worry. Give me the equilibrium constant for esterification reaction. Just that is my question. Is in your past. Just give me the equilibrium constant for esterification reaction. If we go at this level, you might name an esterification reaction. All right, tell me what is happening in esterification reaction. What react? If we go, give me the case if esterification reaction. Now, one name I want to write jam. Okune metigo organic chemistry. In esterification, an acid reacts with what? Alcohol. Alright, there. Acid. The acid in bracket. Acid. There. Acid. Plus alcohol. Okay, don't you shall spell the one. Alcohol. The alcohol. Go to shall spell there. AL. Yeah, alcohol. Thank you. Will give you, is a reversible reaction. That is even condensation polymerization. It will give you what? Ester and the water. This is a esterification reaction. So give me the Kc value. Clean it, mama. Clean it. Here, an acid which an organic acid can be acanoic acid, ethanoic acid, will react with what? Alcohol. Will react with alcohol to give us what? To give us ester. And what? Water. So give me the Kc value. Give me the Kc value. Generally, the Kc is going to be what? Ester and what? Water. So it's going to be like this. Okay? Over what? Acid. Alcohol. Now remember, pure liquid is said to be what? Unity. And water is a pure liquid. So I'll remove water. So the Kc value for esterification is what? Ester over acid times what? Alcohol. Esterification. Finally, write magnitude. Magnitude of equilibrium constant. Magnitude of equilibrium constant. Magnitude. That's the size of equilibrium constant. Magnitude of equilibrium constant. Magnitude of equilibrium constant. Number one, it is constant at a given temperature. Number one, it is constant at a given temperature. Until there, they are asking a magnitude of Kc, or and a size. Number one, it is constant at a given temperature. Number two, I start sharing this. You give us 10 minutes to just write this. I'll do the correction later. Start. Number two, it does not depend on the initial concentration. Number two, its value does not depend on the initial concentration. Number three, its value does not depend on the final concentration. Number four, I said its value does not depend on the initial concentration. Next point, its value does not depend on the final concentration. Idego nkai? Oneki idego? Alright, number one said is what? It is constant at a given temperature. Number two, its value does not depend on the initial concentration. The next one, its value depends on the concentration at equilibrium. Its value depends on the concentration at equilibrium. Each value depends on what? On the concentration at equilibrium. Remember, Kc value does not depend on initial concentration. It does not depend on what? But it depends on what? The concentration at equilibrium. Why they share the paper? I think you have 10 minutes. I will delay the teacher by 10 minutes and add it up to your time. I will not mark it, just I need to have the test. If Kc is greater than 1, if the value of Kc is greater than 1, if the value of the Kc is greater than 1, it means that a large quantity of product is present. It means that a large quantity of product is what? Present. If Kc value is greater than 1, it means that a large quantity of the product is present. Idegia? Okay. Which means that a large number of the reactants, which means that a large number of the reactants have been converted into product before equilibrium is achieved. Which means that a large number of the reactants have been converted into product before equilibrium is achieved. If Kc value is less than 1, it means that a less quantity of the reactant have been converted into product. It means that a less quantity of the reactant have been converted into product before equilibrium is achieved. Lucy Emmanuel, please see us. It's not finished. And when did they went error? Eh? How many? They should shift to the back. Simon, please photocopy that thing. Tell them emergency. Maybe up to 50. Emergency photocopy. I need to go out. Just write your name there. Now we say the magnitude of KC. Listen. If KC value is greater than 1. Now what is 1? 1 is what? 1 is what? Unity. 1 is what? Unity. If the value of the KC is greater than 1, it means that more of I have A and B reacting to give us what? C and D. Up here? It means that more of the reactant, that more of this thing have been converted into this before equilibrium is achieved. You know, A and B reacts to give you this. But before they achieve the equilibrium, they have converted A and B, much of it to C and D. Now, that means that the KC value will be large. The KC value will be what? Large. If your KC value is 1, is unity. If your KC value is big, maybe greater than 1, it means that, in fact, for you to perform an industrial product reaction very well, you need something that will give you a large value of KC. Listen, before you start writing that in your mind, you need something that will give you a large quantity of what? KC. If your KC value is large, that means the thing you are reacting, you are getting more product before equilibrium is achieved. Because once you achieve equilibrium, it will start reversing. Now, if your KC value is less than 1, it simply means that small of the reactant were converted into product before equilibrium was what? Achieved. Before equilibrium was what? Achieved. Now, if your KC value is 1, it is said to be what? Unity. If your KC value is greater than 1, what happens? You are not talking to me. If your KC value is greater than 1, what happens? More of the reactants have been converted into what? Product before what? Equilibrium is achieved. So you see, it's a plus. Is what? A plus. And I told you it is only temperature that can affect the KC value. When we said concentration, what did he do? He shifted the equilibrium position. When we said pressure, what did he do? He shifted the equilibrium what? Position. But once temperature comes in, temperature can what? It shifts the position and the what? Constant. Other ones don't affect the equilibrium constant. Concentration and pressure, what do you have to make equilibrium constant? The only thing that can affect your KC value is what? Temperature. Have it at the back of your brain. And when your KC value is large, that means it is greater than 1. What does it indicate? That in a fruitful. More reactants have been converted to what? Product. So what you are doing, the condition is very good. If your KC value is less than 1, what does it mean? That only a small reactant have been converted to what? Product. This is the magnitude of what? KC. The magnitude of what? KC. Thank you and God bless you. Start writing.